Good afternoon, everybody. My name is Mitch Aiken. This is my colleague, Kitty Cahalan. Some of you we've never met face to face, so you've received hundreds of emails from both of us over the last, 5 months. Some of you going back to early spring. And then some of you worked with us in programs in previous summers that we've offered for our high school students to have experiences here on campus at Caltech. So we're very grateful to all of you for being part of this, for mentors and other supporters of the program. I don't know if we have some faculty and Caltech researchers here and staff for the programs, as well as our students and mentors and teachers. And we're very grateful to reach this day. It's been a very long 6 weeks. I know you all worked very hard, and we're looking forward to hearing what you've learned and what you've experienced this summer. And we're going to go ahead and start with our first group. It's the Matthew Graham group. You can come on up, and our student is Michael Zhang, and we'll let you take it away. Thank you.
Thanks, Mitch. So firstly, thank you to Caltech for supporting this program. I think it offers a great opportunity to high school students to get a taste of what real research looks like at one of the top places in the world. My name is Matthew Graham. I'm a research professor of astronomy here at Caltech. I'm also the project scientist for the State Transient Facility, which is one of our shining star sky surveys that's currently running every night down in Palomar Observatory. I was actually at Palomar Observatory last night, 2 nights ago. I got back yesterday observing with the 200-inch. But it turns out that even though we've been running Palomar Observatory for 76 years, we don't really do a good job at archiving our data. And that was the basis of the project that Michael Zhang, who's been my student working with me this summer. So Michael is a rising junior at Poly, and he has the right skill set to maybe attempt a pilot study to see what an archive might look like for the 200-inch at least, for the amount of data that we have available for it. So we've got tons of data, we just don't know what's in there. And from sky surveys we carry out now, it's sometimes quite important to know what we observed 20 or 30 or 50 years ago. And we have the data sitting on tape, or we have it sitting on the photographic plate in the library yet, but we don't actually know much about it. And so if we could actually create this, it would be a wonderful resource. And this struck me as a perfect project for a student. So I'm going to let Michael tell you all about what he's been doing.
Hi everyone, my name is Michael. And this summer, I worked on creating a pilot sensor database with the 200-inch telescope with Professor Matthew J. Graham. Okay, so to give some background on the 200-inch telescope, so it was first used in 1948, and it was the largest in the world until 1993. And some of its notable achievements included in 1952, Alder used it to correct the distance estimations in Andromeda Galaxy. And this was pretty important because by doing this, he effectively rescaled the entire universe in the eyes of most astronomers. And then in 1963, Marge Schmidt used the telescope to discover the first quasar, which is like a very luminous type of galactic nucleus. And then in 2010, it was used to discover a new satellite of Jupiter called Jupiter Li that's been orbiting the planet. And nowadays it's used almost every other night, which is almost daily in Palomar. As you can see, it's like in between LA and San Diego. So it's a really good contributor to modern day research, but as Dr. Graham said, there's no central repository for all the data. So that's what we embarked on in our 6 weeks. So the premise of our database was to create a relational database in SQL. So the plan was we create 2 tables, a usage table, which would just have like the logs of everybody who's used it, and then a data table, which actually had the actual data of what they got from the telescope. So the usage data came from the public website of so this one. So this is publicly available on like the Caltech website. It doesn't actually tell us any of the data of like the measurements that the telescope did, but as you can see, it's kind of like a sign-in sheet. It just tells us who used the telescope and when they used it. So it's a good starting point because we can use this to basically outline our entire repository. So our first pass was to turn all this into an SQL table. So the way we did that is we wrote a Python script that would screen scrape all of this and turn that into an SQL database. And basically what that does is, if I inspect the page here, you can see that all this is HTML. Let me make that bigger. So we wrote a Python program that just runs through all of this. And you can see all the information is shown in the HTML here. Oh, that's really small up there. Try to make it bigger. Okay, never mind. But basically, we wrote a Python program that runs through all this and turns it into an SQL table. So once we achieve that, we got the first table done. And the plan from there was we would take a date and then link it with another date in the actual data measurement table. So here, the dates are linked up. I know the day is like one off, but for the data table, it's in universal time. So when you convert it to local time, which is what the usage table uses, it's there the same date. So this is how we would link the two tables. Yeah, so that's screen scraping, and yeah, so here for our second table with the actual data, we ran into a little bit of an issue because we thought it'd be a little too ambitious to try to get 50 years worth of data in just 6 weeks. So we pivoted to more of a pilot of a data repository. So what we worked on was all the architecture needed to sustain that kind of data. But so then in the future, all we have to do is just start slowly gathering that data. So most of the data we got was in this file format called FITS, which is an astronomical binary data format. And yeah, it's the most commonly used way to store astronomical data. And here's an example of, it's really small. Yeah, so this is a FITS header just opened up. You can see it's a lot of stuff, a lot of values and variables. But when we put it into our database, we really only put 7 values in, and they're here up here. So this is an example of a data entry that we put into our SQL table. So the first variable I want to talk about is air mass. So air mass can give us a good indication of how deteriorated an image is. So basically what air mass is, it's like a unitless ratio of how much air the light travels through in the atmosphere. So the baseline of one air mass is set to the lowest amount of air, which is directly above the observer's head. And then you can see as the angle, oh, that's really low. Okay. But anyway, as the angle gets less steep, there's more air because the light has to travel through more air as it gets closer to the horizon. And the reason why air mass is important is as light travels through the atmosphere, it interacts with the air particles, which can disrupt it and cause image deterioration. So optimally, you want to observe an object that's very close to directly overhead, because that's where the air mass is the lowest. And then here we also have the two variables called UT shut, which is just the shutter, the time of the opening of the shutter in universal time, and then EXP time, which is the exposure time, which is just like a normal camera where it's just how long the image has been exposed for. And then the two most important data points that we have are RA and declination. So RA stands for right ascension, and it's like the longitude and latitude for celestial objects. So for example, in the bottom left corner, you can see here, this object is being described through RA and declination. So it's very similar to longitude and latitude, it just tells us precisely where this object is. And the final variable of the object name, I found that pretty interesting because some of these objects have, some of the more well-known objects have their own dedicated names, like for example, this one, Wolf 1346, that I did a quick Google search and I got a ton of results. So, but that's only for a small portion of these objects that are more widely researched. So some of the lesser known ones are more, have these like cryptic names. This one here is like J0017, is a bunch of like random numbers, but these numbers are important because they actually tell us a lot about what these objects are. So for example, the J here stands for the J2000 epoch, which is like, it tells us that the location of, that they give us right ascension and declination. So it's the location of when the object was on January 1st, 2000. And the numbers are actually the coordinates of right ascension, but in this format. And when you convert it to degrees, you can see it matches up pretty closely to what we have in our database. And then the second number, which is separated with the plus sign, is the coordinates for declination in the same format. And they're slightly off from what we have in the database because the name can't put decimals, like they don't put decimals in the name. So for example, it should actually be like 0.9 seconds to 1 second, but they don't put decimals in the name, so that's why it's just slightly off. And we also created a prototype front end. Check over here. So it's so small. Okay, so. It's not pretty, but doesn't need to be, all that matters is the functionality. So. The main way people are gonna search for objects in the database are through its location. So we have two search bars and also a leeway value. So basically with the leeway value, the filter is gonna create like a box in space where it's gonna search everything in the database and return all the results of objects in that box. So for example, in this example, I have these two coordinates I search. That's too small, but there we go. It's gonna return all of the values and entries I have here. And then I go back. If I want to show everything in the database, just to show how small we have it right now. If I print everything, we only have around 1,400 results right now, so it kind of shows how like complicated it is to gather all the data together. But this is how our prototype is as it stands right now. And thank you all for listening. Does anyone have any questions? Yeah.
So I presume, is this only for one particular instrument, or do you have you probably can add an extra column to your database for the spectral data for the near infrared imager, I mean, for all this. Right now, I have to say, I think this refers to maybe one particular, maybe just images, but it's very interesting. It's very sounds great.
So if you can definitely add more columns, it would be that was an issue.
Right. Yeah.
Yeah.
Just to see, and just one other question is from the leeway, let's say 0.1. What are the units of that? Is that
Just in degrees, so that's gonna it just creates a maximum value.
0.1 degrees?
Yeah.
Very good. Very good.
Yeah.
Thank you. Excellent.
Yeah.
How many nodes are you expecting once you guys finish everything?
I don't know exactly, probably a few 100,000, maybe 1 million.
Do you think the way you're currently searching spatially will slow down because you have that many?
I don't think so. Because I mean, we're only like 1 million isn't that much for a computer, so I think how SQL is already optimized. I don't think it'll be that big of an issue. Yeah.
Do you plan on expanding it to the other telescopes at Palomar, or how would that translate to a different telescope or database?
I think in the future, there might be some complications switching over, but I think the same concept of just putting values into a table and relating that with other keys wouldn't be that much of a job. Yeah.
Was there a reason you picked SQL over something like JSON? Similar keys and values database system?
I just think that's what I'm most familiar with, so yeah. I will thank you. Oh, yeah.
Is the tool ready now so that the staff is on this can start plugging data into it, or where does it stand right now in terms of putting the?
Oh, yeah. Yeah, so like last night, Graham sent me like 1,000 bit files, and I was just able to just put them into a folder and then press a button, and they all went to that database. So I would say it's pretty ready to run.
What was your biggest challenge? I know you had a busy summer and part of your challenge was on your schedule.
Right.
Other than that.
I think I hadn't worked with much Python before, so getting all the screen scraping stuff it was all pretty new, because I hadn't Python before. I was in Java and C#, so yeah, I'd say that was the biggest challenge.
Anything else?
Oh yeah.
Is your tool open source, and if so, is there a code base available for it?
It's not open source, but I mean I can make it open source, so yeah. Yes.
With other
well, as long as the telescope is using like bits files, then it will work for that. And that's what's most commonly used. So, thank you all.